Okay, so hello everyone and welcome to another Tutte Colloquium. Today we have our very own Walaa Moursi. Walaa received her PhD at UBC Okanagan before doing a postdoc at Stanford and then joining our department a couple of years ago. Walaa works in various areas of optimization, and today she's going to talk about strongly non-expansive mappings. So please go ahead, Walaa.
Thanks, Steve. Okay, so good afternoon, everyone. This talk today is about the so-called strongly non-expansive mapping and notions that are related in monotone operator theory in connection to algorithms through splitting methods. And this is based on joint work with John van der Werf from last year at university and Leon Liu, who is an undergraduate research assistant who worked on this project last summer. So the setting of this talk would be in a real Hilbert space. We have our inner product and the induced norm. So if you feel more comfortable thinking Rn, that's perfectly fine. But you could also allow infinite dimensional spaces, for example, the space of square summable matrix sequences, little l2. And also our setting would involve functions f and g, where our functions would be proper, lower, semi-continuous, and convex. Proper is pretty mild assumption. It means, of course, we don't want to work with functions that can take the value minus infinity. So the function can never be minus infinity. It could be plus infinity, fine, but at least we should guarantee that there is a point where the function value is finite. Lower semi-continuity has a nice interpretation from a topological point of view in terms of the closeness of the so-called epigraph of the function. So you graph the function and take whatever is above the graph. And if this form is a convex function, it's lower semi-continuous. So from the name, it's weaker than continuity. Therefore, this function, which is actually smooth, is lower semi-continuous because it's continuous. This function here, I move the vertex down and I close up I take the epigraph and look at it, and it's clearly closed. But if I actually remove the vertex and put it here, then when I look at the epigraph, this part would not be on board, and therefore it's not a closed set. So the function is not lower semi-continuous. And finally, convexity again has a nice interpretation in terms of the epigraph. So it tells us that the function has a convex epigraph. I look at the graph and take what's above it. And if I get a convex set, then I'm good to go. And of course, the very next example, you look at the quadratic, the very next power, the cubic, will give us a function that's not convex because here is the epigraph and I connect 2 points and I fail to stay in the set. And now I'm going to talk about the first word that would be of interest in our work. So the first word is the word of the so-called monotone operators. And here we have to accommodate with working with these kinds of notations. So when I do double arrows like that, I mean that A could be a set valued operator. So it maps a point to a set and not point to point as we used to. You could actually think of A as a relation. A of X could be empty, could be a singleton, could be like a subspace, as we shall see in the examples. And the graph of A would be all the set of points where we actually see U in AX like that. And now we are in a position to define what we mean by monotone operator. So if I take 2 points in the graph and look at the difference between the points and take the inner products between the pre-images and the images, I get a non-negative number. And the sign of the inner product always tells us what the angle between these two vectors is. So it tells us that these two vectors makes a right or acute angle. And in fact, this is highly connected to optimization because this class of operators, the monotone operators, contains the so-called subdifferential operators of convex functions, matrices with positive semi-definite bursts, not necessarily symmetric. So symmetric matrices would be gradients of convex functions, but you could have something that's not a gradient. In addition to the worst skew operator that sits on the boundary of monotonicity, for example, the rotator in the plane pi/2. So this is why we are interested in this. And I actually forgot to tell you that there is what's called maximally monotone, in which case that if you have this monotonicity property that defines a curve and you cannot add any more points to that curve without destroying monotonicity, then you are maximal in the sense of set occlusion. So this seems too abstract. So let's see what world one is when we drop to the real world on the real line. Now, on the real line, if you look at the definition of monotonicity, and because on the real line we have the beautiful total ordering, then we look at curves that satisfies this inequality, which means that if x is bigger than y, then u must be bigger than or equal to b, which means that we are actually looking at non-decreasing curves. And therefore, something like the cubic describes a monotone operator, but this curve as well, which clearly fails to be a function, defines a monotone operator, and in fact maximal, because we can't extend the graph without destroying monotonicity. But now this function here is a very nice function from a convex optimization perspective, because not only it describes a maximally monotone operator on the real line, it's also a gradient of a convex function. However, the curve on the right, it can't be a gradient, of course, because of this vertical segment here, but it is not way far off from competing with the green curve of the cubic. In fact, it can still have a connection to convex function, even with a gradient to flavor, as we shall see now. So the cubic is a gradient of the quartic, which is a convex function. And now this red curve is, if you want, you can visualize it as a generalized gradient. It describes a graph of the so-called the subdifferential operator of a convex function. And in fact, the function that it describes is subdifferential is the lovely absolute value function, clearly convex. And it's actually differentiable on the strictly positive ray and the strictly negative ray, except at the usual exception at 0, where we have this kink, we have troubles. And in the regions where it is actually smooth and differentiable, the subdifferential operator, which usually defines a set, contains a singleton, and that singleton is just the gradient or the derivative. And then at the 0, if we look at this definition here of the subdifferential, then we are actually looking at all the points or the values u that defines a slope of a line that lies entirely below the graph of the function at this point. And it turns out that anything between -1 and 1 would work for the case of our absolute value function. And that's why we get this monotone curve and not function. So subdifferentials or subdifferential operators are now citizens of world 1. This is the definition of the subdifferential operator. They're maximally monotone, but even more. By Fermat, and because we have convexity, x star minimizes the function f if and only if x star is a 0 of a subdifferential. Now, this is almost a one-line proof. I just needed 2 lines because of the slide. But if you look at the definition here, x star, the 0 is a subgradient at x star, if and only if I had this inequality with u replaced by 0. But that would kill this inner product. And therefore, I learned that for all y in x, f of x star less than or equal to f of y, and therefore x star is a global minimizer. And therefore, finding a 0 of f is equivalent to looking for the zeros of the subdifferential, which generalize what we classically use to look at finding the critical points or the zeros of the gradient if our function is smooth. So subdifferentials lives in the world of monotone operators, and looking for zeros of monotone operators is actually implicitly would be of help if we look at minimizers of convex functions. And now I would talk about world 1 and another notion, which is duality. So looking at an operator A, as I said, you can see or visualize A as a relation, and A is monotone if and only if its inverse is monotone, where you look at the inverse by just inverting the points in the domains and the range. So just inverting the order of pairs. And again, it's very possible that you get something that's not necessarily a function. That's perfectly fine. But this actually has a very nice interpretation from a function perspective as well. So if A is a subdifferential operator, then the inverse in this case is also a subdifferential, and it's the subdifferential of the so-called differential conjugate of the function. And we can look at the example that I showed you 2 slides ago. So this is my A, it's x cubed, and it is actually a gradient of this convex function. And it's a nice invertible curve because it's strictly increasing, and I can look at its inverse, which is the cubic root of x, and the cubic root of x as a derivative integrating yields the differential conjugate, which is this function here with a power of 4/3. So worlded 1 contains monotone operators, and the dual notion would always stay in worlded 1 as well. And now, and that's one of the key things that we actually care about in this talk, we look at if we have a stronger notion of monotonicity. And just like monotonicity responds to convexity in the optimization world, stronger notion of monotonicity also corresponds to stronger notions of convexity. So suppose that A is an operator on X. We say that A is uniformly monotone if this is the inner product that we look at if we want to check monotonicity. Now, if this inner product is lower bounded by a function phi that is increasing, always bigger than or equal to 0 and vanishes only at 0, then we get a better bound on the right-hand side. It will keep monotonicity, but even in a better or a uniform way. And if we upgraded this function to have it as the 1/2 norm squared, then we get the notion of the so-called stronger monotonicity. And again, the correspondence to the world of functions is there. So uniformly monotone operators contains the class of uniformly convex, the subdifferentials of uniformly convex functions. And likewise, the class of strongly monotone operator contains as a proper subclass the class of subdifferentials of the so-called strongly convex functions. Example of uniformly convex is the quartic power type 4 in the modulus. Example of strongly convex is the quadratic with power type 2 in the modulus. So I'm now done with talking about worlded 1, and I will move now to worlded 2. So in worlded 2, I talk about something completely different in nature. No longer set valuedness, nothing to worry about being with restricted domains. I look at a mapping that maps X to X. And we say that T is non-expansive if it's Lipschitz continuous with a constant at most 1. T is an alpha averaged operator for some constant between 0 and 1 strictly. If I can write T as a convex combination of the identity map, the map that maps each point to itself, plus the non-expansive map. And because the norm is actually positively homogeneous, and because N is non-expansive, I can use the triangle inequality and see that the averaged guys are also non-expansive. So this is a subclass from this. And then finally, T is a Banach contraction if it is Lipschitz with a constant that is strictly less than 1. And if you want to actually have an intuition how these maps work, then here is a non-expansive mapping. If this is X minus Y, then the image Tx minus Ty would stay in the ball centered at 0 with the radius at most norm X minus Y. Average would be in that ball as well, but it will not touch any of these points except this one. And I will show you why in the next slide. Banach contractions would be in a strictly smaller ball inside the bigger ball with radius X minus Y or norm X minus Y. Why do we need these different notions? Well, this has something to do with the iterative behavior of these methods. So let's take T be a mapping from X to X, and I remind you that the fixed point set of T is the set of all points that does not change under the effect or under the application of T. So it maps any point to itself. This is a set of fixed points. And I start at an X0 and update my sequence by applying T recursively. I create a sequence Xn, and if the fixed point set of T is non-empty and T is non-expansive, then the very best we can guarantee is that that sequence stays bounded. We can't talk about conversions because think of the minus identity map that maps a point to its negative. You're here, if you start with a non-zero vector, you will keep jumping, bouncing back and forth between the point and its negative. You get a sequence of x0 minus x0 and so on and so on and so on, and you will never converge. However, if you are averaged, this non-trivial contribution from the identity map would guarantee that you could be here, so not necessarily contracted, but that would avoid you from getting to that bad minus identity. So average operators are nicer. If they have a fixed point, they converge weakly to that fixed point. But even better, if you have a Banach contraction, then you don't need to assume existence of fixed points because you get it for free. And even better upgrade, Xn in this case will converge strongly instead of weakly, which is something that you only worry about if you work in infinite dimensions. And on the top of that, you get a linear rate of convergence. So these were the two main worlds. And then there are key players that will work back and forth between the two worlds. So if A is maximally monotone, we define this very important object, the resolvent of A, to be the inverse of the identity plus A. And the example of the resolvent in convex optimization is that the prox of the function f. So if you have a convex function f, the prox operator is just the resolvent of the subdifferential. And now in this talk, we won't focus on the resolvents, but we will focus on the reflected resolvents or the reflected prox operator, which is defined by this. The reflected prox operator or reflected resolvents, their fixed point set are the same as the set of zeros of the operator. And I remind you that we're looking at the zeros of the operator A, then we are looking at minimizers of a certain function f. And very beautifully, the reflector of the inverse, which now we are talking about the dual world, with an algebraic proof of one line, you can see that this is a negative of the reflector of the original operator. Now, this seems too abstract, so I'm dropping to an R2 example just to show you what these objects look like. So let's take on the real line, the x-axis, and I take the function f to be the indicator of the x-axis. The indicator function is very popular in constraint optimization. And what the indicator function does is that it treats the points in the set very well by giving them the value 0. And it really penalizes those outside the set by sending them to infinity. The conjugate is the indicator of the y-axis. The subdifferential a of x is this operator that maps any point in U to the entire y-axis. So set valued, as you see, x is mapped to the y-axis. And if the point is not in U, then the subdifferential would be empty. The dual notion will do exactly the same with U and U perp flipped. The resolvent of A is just an orthogonal projection onto the x-axis. So it's just this matrix here that maps any point alpha beta to alpha 0. And the reflected resolvent is the reflector through the x-axis. And here's a visualization of this. So this is my linear subspace U, and here's x bar. My resolvent will project here, and I get alpha 0, and I go twice as far, I get the reflector. And here is the resolvent actually of the inverse, which is the projection onto the orthogonal complement, and I go twice as far, get the other reflector. The reflector of the inverse, as you see, is the negative of the reflector of the operator. So what I actually explained in a very abstract fashion is a generalization of this in a very nonlinear, much more general framework. So how close are these two worlds? They are super close. They are actually twin worlds, even though it doesn't seem like that, but they are twin worlds. So in the world one, we talked about monotone operators, maximal monotonicity of the operator and its inverse, and we have an if and only if, but there is a correspondence. Maximally monotone operators are characterized by non-expansive reflectors and vice versa. Every non-expansive mapping defines a maximally monotone operator, and in the dual, you look at the reflector of the inverse, which is minus t. Non-expansiveness does not care about the sign, so everything goes through very beautifully. Now, when we actually, that is the base model. monotonicity. If we start upgrading the properties of the operator, we should expect to have some upgrades in Walaa 2 as well. And indeed, if A is a strongly monotone, we get that the negative of RA has a very nice property that it is averaged operator. The dual to strong monotonicity is called co-coercivity. I won't go through that, and we don't need it, but I just wanted to show you that there is a dual notion, but not like monotonicity. The dual is not the same, but you get on the other side, and thanks to the fact that I can relate the reflectors of A and inverse, we get that the reflector of the dual is averaged, which is great. And now, here's another case when you actually assume that the operator A and its inverse has a strong property together, they join forces and we get something really decent.
Hi, I have a few plumbing issues at home that I'm looking to get resolved. Like there's a valve that needs to be replaced. I mean, it feeds into the dishwasher, and also sort of the inlet valve for the dishwasher itself. And then there's a faucet replacement and a...
Ashwin, I think you got your
and also
So we
Sorry
get
about
now,
that. Go ahead.
That's perfectly fine. So we get now that if both properties at the same time are on one operator, the operator joins forces, and we get that the reflector in this case is a Banach contraction. And that leads to the fact that we have very nice properties in Walaa 2, assuming that we have an upgrade in Walaa 1. Now, the question is, uniform monotonicity is general notion, as I talked about that earlier. So if we have the more general notion of uniform monotonicity, what can we say about the dual? What can we say, what happens in Walaa 2? What are the kinds of upgrades that we get in this case? So if we look at this, the reason I suggested uniform continuity here is the fact that there is always analogy to what happens in the function case. And in the functions, if we have a uniformly convex function, then its conjugate would be differentiable and will have a uniformly continuous gradient and vice versa. So that was what brought this as a candidate for the dual property, but we don't know. Also, and inspired by this, if we have a super nice with both A and the inverse has a nice property, can we say something on the other side? So that was actually the motivation behind exploring this. But again, this looks, again, very abstract because I need to show you why this is actually important. It has a motivation from an optimization perspective, in fact, because in optimization, we look at minimizing sum of two functions as a typical convex optimization problem. In fact, if you have constraint optimization problems, then you minimize objective subject to constraints. You can write this as minimizing your objective, and G here will be the indicator function of your constraint set. So this is a typical setting that we see in constraint optimization. By Fermat, we're looking at zeros of the subdifferential of f plus g. And we need some constraint qualification to have the sum rule hold. Unlike gradients, things are not that simple when we leave the smooth world, but assuming that everything is fine, this setting, looking for a zero of sum of two subdifferential, is perfect for splitting methods. And how splitting method works, it works by iterating the so-called splitting operator. Some examples are Douglas-Rachford, which iterates this operator here, and Peaceman-Rachford that iterates this operator, and forward-backward that iterates this operator. All of these operators are functions of the proxies. Let me tell you that Douglas-Rachford is the most robust, doesn't require much. It only requires our standing assumptions of convexity. Peaceman-Rachford, unlike Douglas-Rachford, requires something more. Forward-backward requires more, but it has the advantage that it has one forward step, which is cheap. So one thing that you might actually comment on is that Douglas-Rachford doesn't require much, and computationally, it looks like this is the expensive part that requires calculating proxies. So you might say, okay, if this doesn't require, why I would actually think about Peaceman-Rachford at all? And I will answer that one slide down the road, but let me work in a more general framework. So in this talk, I will fix A and B to be maximally monotone. And the problem we look at is finding a zero of the sum of two maximally monotone operators, which is exactly the setting on the previous slide if I actually restrict A and B to be subdifferentials. And these are the splitting methods that I'm going to talk about. So I iterate these operators. The resolvent here is just generalized the prox. Everything is just whatever fits to solve this monotone inclusion will work for our optimization problem of minimizing F plus G. Now, this is a Douglas-Rachford operator. This is a Peaceman-Rachford operator. Let me show you two scenarios. Suppose that RA is a Banach contraction and we have a characterization when this happens. Now, Peaceman-Rachford operators tells us that this composition will remain a Banach contraction with a constant beta. Whereas using the triangle inequality, and again, the fact that this is Banach contraction, I also will learn that Douglas-Rachford will give us another Banach contraction, but with this factor. So even though in general, Peaceman-Rachford is weaker in terms of robustness than Douglas-Rachford, but if we know more, if you look at these two constants, you will see that Peaceman-Rachford in this case is a clear winner because the constant is much better. That's one scenario. Another scenario, take A to be the zero operator, the gradient of the constant of any constant function, and B is the inverse of A, which is the normal cone, the singleton zero. When I calculate the reflective, that's pretty straightforward. It will give you the identity and minus identity, and their composition would be just to the minus identity. The n by n matrix in Rn, negative ones along the diagonal, 0 up and down. Now, as I said, minus identity is the worst possible non-expansive mapping you could actually look for. But if you average it with the identity, magically you get the best possible contraction you could aim for. So properties on RB and RE, and the way they are combined together and the way they behave after averaging them with the identity could lead to actually much better rates of conversions. And therefore, I'm hoping to give you insights about this question. What do we look for? But I don't have answer. And because I don't have poses, I don't prefer to use it with Zoom. You probably see my answer at the very bottom, but let me actually elaborate further. So summary of some of the known results. We have a characterization when the reflector is a Banach contraction. In this work here by Getzels and Boyd, we get a Banach contraction in optimization setting. And in this very beautiful paper by Getzels in 2017, this actually has much more. In that paper, he introduced the notion of the so-called negatively averaged. So you look at the property where this composition, it's negative, is an averaged operator, in which case you get something really nice. But if you observe in the first three cases, all the properties that we had in the monotone world, we looked at properties that were in world 2, Banach contraction, averageness, negative of averageness. And now when we started this work here, we looked at the case when A is Lipschitz continuous operator, but not necessarily a subdifferential. And surprisingly enough, we actually got stuck here for some time because the reason is when we looked at this, we were looking at properties, the candidates that we looked for were all in world 2 as we expected, because this is where the reflectors live. They live in the class of non-expansive and all that. Surprisingly, the right property that we looked for does not actually even live in world 2. It lives in world 1, not quite even in world 1. It lives in like sub or I would say like underground world 1, so you can consider it world -1. It's called hypomonotonicity. So if it's monotone, if it is of monotone flavor, but weaker than being monotone. And therefore, the question to what we are looking for, I really don't have a good answer. It's hard to conjecture, but it's so much fun to explore. And the key player in this work is the Minty parametrization. So what does Minty do? Minty's parametrization gives us a tool to parameterize the graph of a maximally monotone operator E. Take an X in your space and hit it by the resolvent and the reflected resolvent, and you will get the point in the graph of E. So it parameterizes the graph in a nonlinear fashion very nicely. And this boils down to the known identity in convex optimization, the prox of F plus the prox of the conjugate is identity. In the special case, if F is the indicator of a cone, then you end up with the projection onto the cone plus the projection onto the polar cone gives you the identity. And here's a nice example in R2. Take it to be the non-negative orthant. The polar would be the non-positive orthant. You take X bar, project. You get this point here, and you get this point here. Clearly, they add up to X bar. And in the very special case, if your cone is even more and more special and you make it a closed linear subspace of X, then you just recover the decomposition of a vector onto the subspace and its orthogonal complement. So Minty does generalize this in a super beautiful way, decomposes any vector X onto two sets, the domain of the subdiff or the domain of the monotone operator and the range. These sets, unlike U-perb, need not be closed, need not even be convex, even if they come from functions. So Minty's parametrization is our bridge to go to where we want. Because if we look at this, we want to actually, in exploring non-expansiveness or like any contractivity behavior, we look at comparing this inner product and see what we get on the right-hand side. So by Minty, if I set T to be the reflector, I look at this green term here, and I start using the parametrization, write these two norm squares as difference between two vectors and the inner product of the difference between the vectors and the sum of the vectors. And that will give me this inner product here. Now by Minty, this is a point on the graph, and the blue pair as well is a point on the graph. And now, if A is monotone, I know that this is bigger than or equal to 0. Perfect, follows the script. This is non-expansive then. And if we have a stronger notion like stronger monotonicity, I get a lower bound that's actually like that. And this is actually a very starting point to proceed. So using Minty's parametrization, we start looking at the class of uniformly monotone operator. Okay, what do we get? Here's what we had on the left-hand side, and putting everything in place, this is what we get on the right-hand side. Looking at it in the first place, it doesn't look like we have seen a clear correspondence where this actually corresponds to in the world of non-expansive mappings. So we started digging, and it turns out it has a connection, but not with a correspondence, to a class of operators called strongly non-expansive, introduced by Brock and Reich. So this class is defined as follows. If xn minus n is bounded, and you have the difference in norms between these two sequences go to 0, then you can throw away the norms, and the difference between the actual points will go to 0. And if we carefully look at this characterization that we obtained, we can show that if A is uniformly monotone, then the negative of the reflector satisfies that it is strongly non-expansive. Well, as I showed you earlier, we looked at characterization. Characterization is the true power because it allows us to talk about composition, so many things. So we start getting more greedy. Can we get characterization? It didn't seem to be possible, and we thought, okay, maybe we need actually to define a new class of operator, and we did define the new class of operator called super strongly non-expansive. And that class assumes that if the difference between the squared norms of sequences of this form goes to 0, then you can throw away the squared norms, and the difference, the actual difference between the vectors goes to 0. And the reason we called it super strongly non-expansive is that it is actually a proper subset from strongly non-expansive. And I say proper because we have a counter example that shows that the other direction does not go through. However, on the real line, and again, using the advantage that on the real line we have total ordering, we get that the two classes coincide. Now, let's put the pieces together and see what we have. A is uniformly monotone with a modulus phi if it satisfies this inequality. And now remember, this is a definition of super strongly non-expansive that we introduced. I put it in gray because I'm just reminding you. And now I will look at the case when minus t, not t, is super strongly non-expansive. So I applied this definition with minus t replaced by t, or with t replaced by minus t. And this part of the implication, the norm square or the norm doesn't care about the sign. This part of the implication, the minus becomes a plus, and this is what we get. And taking this and looking at what we have here, when this goes to 0, and by our assumption on the modulus, we learn that this will also go to 0 because it's bigger than or equal to 0. And because the modulus vanishes only at 0, we learn that whatever is inside will go to 0. And we learn that the minus of RE is super strongly non-expansive. And one more implication, it must be strongly non-expansive then, because we proved that in general, all super strongly are strongly. And finally, we now have a correspondence. So we have that uniform monotonicity corresponds to super strong non-expansiveness of the negative of the reflector, and 2 implies 3. So I'm going to actually show why 2 implies 1, because on the previous slide, in a compact way, I showed you that 1 implies 2, implies 3. So I'll only show you why 2 implies 1. Now, I will argue by contradiction. Let's assume that E is not uniformly monotone, but still have its reflector with a negative sign super strongly non-expansive. But this will guarantee that we have sequences of this form in the graph of A, such that En minus Bn stays away from 0 by a certain positive epsilon. But we still have this inner product that comes from points in the graph of A goes to 0. And now this step looks highly technical. I won't read like the sequences, but all I can say is that I used Minty to go from this sequence to something on the reflector. So that is by the power of Minty. So I put this on the side now, and my goal is to show that this difference in norm squares go to 0, because then I will use it with the super strong non-expansiveness definition to throw away the norm squares and drop to the actual points. So this difference in the norm squares, the negative would not be impacted. So I can write it like that. Again, 2 norm squares, you can actually decompose them into inner product of the sum with inner product of the difference. And this is what I did here. And using Minty again, I concluded that this actually is just this brown inner product. But this brown inner product actually goes to 0. And therefore, if you discard all these intermediate steps and follow the red limit, then this is the if part of the definition of super strongly non-expansive. If this goes to 0, you can throw away the norm squares and work with the vectors inside, and you know that this goes to 0. So this is what I did. I throw away the norm squares, and this must go to 0. It won't hurt if I multiply with this 1/2. I will still go to 0. But if I do this, then this is exactly An minus Bn. And I conclude that it goes to 0. But this is absurd because I know how on earth would you have this going to 0? And we know that they are bounded away from 0 by a positive epsilon for all n. So we get a contradiction, and this means that we close the circuit, get our correspondence, and we now have a class of operators that corresponds to the class of uniformly monotone operators. I have to say that we were super happy with these super strongly non-expansive operator. And the reason is, this is how we defined super strongly non-expansive. Minus T would reflect in a plus sign here. The reason we were very happy with it is that there is a correspondence between them and the class of reflectors of uniformly monotone, which means that if I compare these two definitions, there is a hidden modulus here. Now, in splitting algorithms, as you have seen, we look at compositions of the form RB composition RA. And with this modulus, we looked at it before getting the correspondence. And with this modulus, it wasn't clear at all how would we proceed with the compositions. So suppose that we have 2 super strongly non-expansive now with this new equivalent, clean, modulus-free definition. The proof is actually these 3 lines. Take 2 super strongly non-expansive and look at their composition. And of course, the composition would stay non-expansive because each of them is non-expansive, Lipschitz one. Now, suppose this limit goes to 0, if I want to verify that the composition is, again, super strongly non-expansive, then I want to verify that this limit goes to 0. And this is what I'm going to do. So I take this limit and write it here. And in between, I will sneak in a handy 0. And then I will regroup differently. So I take those two together and those two together. In general, it's impossible to decouple a sum of two sequences going to 0 into each sequence go to 0. But because this is non-expansive, we learn that this is bigger than or equal to 0. And similarly, this term also is always bigger than or equal to 0 for each n. And therefore, I can decouple this limit into two limits. This on its own goes to 0, and this on its own goes to 0. And now, T1 is super strongly non-expansive. So I can throw away the norm squares and get a limit. And similarly, for the second one, I can throw away the norm squares and get a limit. And now that handy 0 that I sneaked in earlier pays off very well and gives me an even better 0 this time with no norms. And when I add the two, I throw them away and we get that this limit goes to 0. With the modulus definition, how easy this is, I don't know. It could be doable, but we give it a trial before actually we get the new characterization. It wasn't actually very easy. So we now actually look at a new definition of the so-called contraction for large distances. And we say that an operator T is a contraction for large distances if whenever the points x and y are away from each other a distance of epsilon or more, the difference or the difference between their images is bounded by k epsilon, which is a constant depending on epsilon, but still strictly less than 1 times the x minus y. So it's some sort of like, I would say Lipschitz or contractivity, but it depends on the distance between the points. And now something really nice happens. We have seen that super strongly non-expansive are strongly, but the opposite is not necessarily true. However, if we assume that both T and minus T are super strongly non-expansive, then this is equivalent to assuming that both of them are strongly non-expansive. And both definitions or both assumptions would lead to the fact that T is a contraction for large distances. So that is really nice and cute because that would lead us to the main duality result in this work. So we showed a few slides ago that if A is uniformly monotone, then the negative of the reflector is super strongly non-expansive. And we have this very beautiful connection between the reflector of the inverse and the negative of the reflector. And that's why we actually look at operators of the form T and minus T. And here I will borrow the words of my collaborator, John van der Werf, where he says that the story here follows the script. And he says follows the script because it actually has an analogy to what happens in the convex function world, as I will show you in the next slide. So now we have these bunch of equivalences. A is uniformly monotone and uniformly continuous. It's similar to the case A and the inverse are strongly monotone, but in the uniform framework now, if and only if the reflector is a contraction for large distances. So we knew from the beginning, we cannot aim for Banach contractions, the global property, because it's a characterization of when A and A inverse are strong. So definitely we know that we are not there. But this is, it turns out that the weaker property that we will achieve in this case is a contraction for large distances. And that's if and only if the operator and its inverse are uniformly monotone, if and only if they are uniformly monotone and uniformly continuous. The reflectors in this case are both strongly non-expansive and super strongly non-expansive. And here I would like to quickly comment on the following. What we succeeded in, what we had no luck, and we proved that we cannot generalize. So in the function world, the subdifferential is uniformly monotone if and only if the differential conjugate of the function is smooth and has the uniformly continuous gradient. We were able to show that one direction would still go through for monotone operators. So if A is uniformly monotone, the inverse is uniformly continuous, but the opposite is not true. So we don't get the if and only if. And the counterexample that kills it is the skew operator as usual. However, What goes through is the self-duality. So if both F and F star are uniform, if F has both the fact that, or the property that is uniformly convex and has a uniformly continuous gradient, then its conjugate will have the stronger property of being uniformly monotone with uniformly continuous gradient as well. And this is what we proved in the previous slide. And that is actually very nice because it gives us some insights when we can get something with a contractivity flavor. And here is an example to show that these classes are really distinct classes of operators. So we look at this function here, and the function f given here is differentiable, and the derivative is continuous and increasing, strictly increasing actually, and therefore we can verify that the function is uniformly convex on bounded sets. However, the segments where we have unbounded sets are segments where the function is actually even better. It's actually strongly convex. And therefore, the bounded sets part together with these segments guarantees that f is in fact uniformly convex. And the nice thing is that it's also, if you want to learn something about the conjugate, because of the duality, we want to see whether or not f star is also uniformly convex. Do we need to calculate f star? We can, but in fact, we don't have to. All we need to verify is that by the characterization, we need to verify that f has a uniformly continuous gradient. So we actually look at f, find the derivative, and verify that it has a uniformly continuous gradient, and that's fine. But we want to prove that f and f star, none of them is strongly convex, just to show that we have borderlines between these classes. And to see why f is not strongly convex, look at this segment here with the power type 4. Really bad modulus cannot be of power type 2. So f cannot be strongly convex because of this segment. If you want to kill the strong convexity for the conjugate, then it's equivalent to kill the Lipschitz continuity of the gradient of f. And this is done by killing it through this segment, because if you look at the gradient here, it's x to the power of 1/2, which is clearly not uniformly continuous. So that was actually one example to show that these are distinct, different classes of operators here. We have another example from another perspective, this time starting from the reflector, just showing that, yes, we can have a non-expansive operator that's not a Banach contraction, because if you find the derivative, you will find that at 0, we have t prime of 0 gives us a cosine, which is at 0 has a value 1. So we cannot be contractive, but we can prove that this is a contraction for large distances. And we solve it backward. I will skip through that. We had everything, A, inverse F, F star, all that. But the main result here is the fixed points for contraction for large distances. Just like Banach contractions, we were able to show that contraction for large distances will have a unique fixed point, and every sequence created by iterating these operators will converge strongly to that unique fixed point. And that was actually related or connected to the correspondence with uniformly monotone operators. And now, if we want to say something about algorithms, then we actually look at compositions. And what we were able to show is that we looked at compositions of different forms, because here we care about cases when the operator is strongly non-expansive or its negative is a strongly non-expansive. And it turns out that the composition behaves more in the flavor of multiplications or products. So if both of them had negative sign, then the composition would have the property with a positive sign. And if one is positive and the other is negative, the composition would have the property with a negative sign, and so on. And finally, we proved that if we have a non-expansive mapping and you take a composition with contraction for large distances, then the composition would remain a contraction for large distances. Difficulties in the proof is that you need to be careful here. It's not like Banach contraction, the order matters. If the inside one is the one that's for large distance, it becomes easy. But if the outside one, you need a little bit more work. And now I wrap up with the application to algorithms. So the first application is to Douglas-Rachford algorithm. So assuming that A is uniformly monotone, whatever I wrote in gray is what's classically known in the theorem. If the sum has a 0, so think of the sum of two functions that has a minimizer and the sum rule holds, which means that I'm looking at two subdifferentials here, and the sum of the subdifferentials has a 0. Then the fixed point set of t is non-empty, and when I iterate, I create a sequence xn that converges weakly to a point in the fixed point set of t, whereas what we call here the shadow sequence that is created by shadowing the sequence xn by the resolvent will converge strongly, in this case, to the unique 0 of a plus b. Now, the upgrade we get as a product of our results is the following. If one of the operators, the inverse of A or the inverse of B, is uniformly monotone, then in this case, T becomes contraction of larger distances, and therefore it will have a unique fixed point, and the sequence Xn will now converge strongly to that unique fixed point. For the case of Peaceman-Rachford, we get an even better upgrade. So again, Peaceman-Rachford iterates to this operator, and we have two sequences again. This is what we call the governing sequence, and this is what we call the shadow sequence. And now, whatever is in gray, again, is a classical result. The set of 0 of A plus B is a singleton, and the fixed point set is non-empty. We can say nothing about the governing sequence in general for Peaceman-Rachford. However, the shadow sequence will always converge to the desired solution. Now, if we assume now that B is uniformly monotone, then we get something better. We get that T is a strongly non-expansive, and therefore the governing sequence will converge weakly to some fixed point of T. And even better, if A is a strong guy and has a property that it is uniformly monotone, and its inverse is uniformly monotone as well, then we get that T is a contraction for large distances, and the governing sequence will converge strongly this time to the unique fixed point. So here are two examples just to show you what kind of upgrade we obtain.
Hi, Walaa.
Yeah.
If you could finish in the next few minutes, that would leave time for questions.
I only have 2 slides, so I'm done.
Great.
Yeah. So these are the two examples that shows how Peaceman-Rachford has been upgraded. So we work with the normal cone of 0 and the 0 operator. So the operators are the opposite of each other. And I think this is an example that I actually did earlier, so we just revisited here. The composition of the reflectors would be the composition of the identity map with the minus identity map, which will give us the identity map. And I start iterating the operator at a non-zero vector, I will never converge. I'll keep jumping back and forth. So this is the case. One operator is even better than being uniform. It is strongly monotone, but the other operator is not uniform. And that's why the governing sequence fails to converge here. And the other example is actually the nice one. The governing sequence could converge weakly, but not strongly. So here we have to have some fun with infinite dimensional spaces. So let's work with little L2. And let's say take our En to be the canonical basis or the shadow basis, 1, 0, 0, 0. So 0 everywhere and 1 in the nth degree. And I take R to be the right shift operator. So it's the operator that shifts us, gives us 0 here, and everything continues. So clearly R is an isometry, therefore it's non-expansive, and therefore it defines a maximally monotone operator if we solve backwards. And A is again the best super strongly non-expansive, strongly monotone operator ever. Therefore it's uniformly monotone. And I calculate my reflectors, and my reflectors are the minus identity and minus the right shift operator. And I take the composition, and that would give me just the right shift operator. What does the right shift operator do? It will act on E1, giving me E2, because it will shift it by 1. And applying it iteratively, it will create the sequence E1, E2, E3, and so on and so on. And this is a sequence that converges weakly to 0, but not strongly. And that was the talk. This is the paper to be on archive soon. This is a fantastic reference for convex function, and this is original paper by Reich.
Okay, let's thank Walaa for her talk. Are there any questions? For those in the room here, we had some problems with the audio setup last week, so we have a handheld microphone now. So if you have a question, just raise your hand. I can pass it to you. Anyone here? Anyone online?
So for the Peaceman-Rachford, how do the parameters come in?
This is a very good question. So the parameters come in the following. So it comes in the step length, Henry. So minimizing a function f plus g is the same as minimizing gamma f plus gamma g, where gamma is bigger than 0. And this is where you see the parameters coming into play. However, I just need to be careful here with something. Sometimes in the literature, some people use Peaceman-Rachford to denote what the so-called, let me add one more page quickly and explain this. So some people would use Peaceman-Rachford to say that an operator of this form, 1 minus lambda identity plus lambda RB array. This is, in my opinion, is more known as relaxed Douglas-Rachford. The fixed point set of this operator, whenever lambda is between 0 and 1, this is an averaged operator because this is non-expansive. The fixed point set is the same. So sometimes when people use this for Peaceman-Rachford, the parameters comes into play by playing with the averageness constant lambda between 0 and 1. So there are two things, and the paper by Pontus Gisselson in 2017, the one that I referred to, is actually very comprehensive for the already sorted cases. So he had their optimization over parameter that involves step length and also over parameter that can use for averaging like that, of that form. So what is the optimal lambda as a function of the strong convexity or the Lipschitz constant or the combination of those. So what is the optimal lambda and what is the optimal step length in case you do R gamma B, R gamma A? What is the optimal gamma in this case? Does this answer your question, Henry?
Yeah.
Okay, other questions? I guess maybe more at a meta level, you said you have a situation where conjectures are hard, but experimentation is fun. So how do you decide what kind of experiments you want to run to find your conjectures? And related to that, maybe what kind of computational tools do you use? Like I saw you had GeoGebra stuff.
So, okay, so here, it depends actually. So when we actually did the one which had the non-expansive guy, the non-expansive only and not a subdifferential or not a gradient, the candidate that we played with mostly was this Q operator. And the thing is, like, you play with this Q with different operator and see what's going on. And I used Mabel for that one. I remember Mabel was the one that we actually relied on a lot for that one, because you want to actually look at, I mean, on the other side, you want something linear so that you see a clear rate. And in R2, and you want something that like really on the border of this, so you tighten your results. So for that one, we used Mabel. GeoGebra would be nice if you want to monitor convergence, because you could play nicely with the starting point and see how the starting point could get crazy if you mess things up, or how the starting point would behave so nicely. So GeoGebra would be nice if you want to monitor the sequence and its behavior. Again, it depends on what you are looking for. If you're looking for rates, then that is the one. If you are looking actually at the behavior of convergence, so like locating what the limit is, GeoGebra would be nice, because sometimes we get greedy and we want to guarantee that the limit is the closest to the starting point, for example. So, but this, I would say that those are mainly Mabel, GeoGebra would be the two main things. Sometimes Mathematica as well.
Okay, great. If there are no other questions, the only other thing I can think of is whether or not Ashwin fixed his dishwasher, and that's probably better answered after we stop recording. So let's all thank Walaa again for a great talk. So next week we